Hello Year 12 Methods students. In this video we're going to be looking at the graph of the derivative function. So when you have an original function and you try to sketch the graph of the derivative function. And a couple of key terms here that we're just going to define at the start. When we talk about the gradient function versus the original function, if we think of the original function as being f of x, which of course it doesn't always have to be called f of x, but that's probably the most common name for a function, then the gradient function, well, obviously we're talking about f dash of x. But in this section we're just thinking purely working graphically, and maybe we don't even have the equations that represent f of x or f dash of x, we're just working directly from a graph. And so when you're trying to go from the original function to the graph of the gradient function, there's really three key things that you're looking for. On the original function, anywhere where any values of x where there is a stationary point, well, what that will equate to on the gradient function is an x-intercept. Okay, so the gradient function will have an x-intercept whenever the original function has a stationary point. And as we go through examples, you'll hopefully see why this is the case. Any values where the original function has positive gradient, the gradient function will be above the x-axis. And for any values of x where the original function has a negative gradient, the gradient function will have values below the x-axis. Okay, so these three sort of things here are for f of x. These three things are for f dash of x. Okay, let's get stuck into an example and hopefully things will kind of come together as we go through it. So we're given a graph here in example 8, we're given a graph of f of x, and on the same axis we're asked to sketch the graph of f dash of x. All right, let's just have a look at those three kind of key sections of the original graph. Remember that the three things we're looking for is where do we have stationary points, where do we have positive gradient, where do we have negative gradient. If we look first, and I think it's always a good idea to look first for where are the stationary points, and I'm going to color the stationary points in yellow here. We've actually got three of them on this graph. We've got a stationary point when x equals -1. We've got a stationary point when x equals +1. And we've got a stationary point over here, a stationary point of inflection at x equals 4. Okay, if we look for the sections where the gradient is, let's say positive, okay, so where's this graph going up, where are the values increasing? Well, you can see that to start with, if we read from left to right, start with they're coming down, but in this section here, in between -1 and +1, we've got a positive gradient because the graph is going up, okay? After x equals 1, it seems to be going back down, then we know it's got this stationary point, and then it's going down again. So the rest of the graph here has got a negative gradient, and I'll do that in red or pink or however this comes up on camera. All right, so negative gradient from the left coming up to x equals -1, then a negative gradient between x equals 1 and x equals 4, and from x equals 4 and to the right, we've got a negative gradient again. Now these sections kind of each correspond to, I guess, a different feature of the graph of f dash of x. Now, when we sketch the graph of f dash of x, we know that f dash of x is really the gradient, right? It's the rule for the gradient. But we're really now thinking of the y-axis as being f dash of x. Okay, so when we think about how all of these sections are going to translate to a new graph of f dash of x, well, really we're thinking about the y-axis as representing the values of the gradient. And so those three stationary points, we know that that's where the gradient equals 0. So on our new graph of f dash of x, those 3 points are going to be x-intercepts. Okay, so these three stationary points will be x-intercepts on our graph. I'll just do this really faintly in pencil. The sections where the gradient is negative, our graph of f dash of x must be below the x-axis. Okay, so in this section here, we're going to be below the x-axis. In this section here, we're going to be below the x-axis as well. And in this section here, we're also going to be below the x-axis. Wherever the gradient's positive, our graph of f dash of x is going to be above the x-axis. Okay. The other thing that we should try to consider, and it's hard to get this perfect, but you should try to consider how steep the gradient is. Because if the gradient's really, really, really steep, then your graphs should be well below the x-axis or well above the x-axis. If the values are relatively flat, they should be closer to the x-axis because the gradient's closer to 0. So if you think about just sort of this little section here between x equals -2 and x equals -1, I'm going to actually go from just before the stationary point here, just before this stationary point. If it was like negative 1.1, you can see that the gradient, it's still negative, but it's pretty flat, right? Because it's getting pretty close to 0. So on the graph here, on the graph of f dash of x, we might have a point that's just below the x-axis. But as we move to the left, as we move towards x equals -2, that gradient's getting really, really super duper steep. It's getting much more negative. So even by the time we get over here, our values of f dash of x may be way down. They're below the x-axis because it's very negative over here, okay? And so for this section, we might say, okay, well, looks like, and again, I'll just do this faintly and then I can kind of make a better job of the graph hopefully after that. But the graph of f dash of x might be doing something like this. It's really negative to start with, and then it's coming up towards 0, and when it gets to x equals -1, the gradient actually reaches 0. Okay. After that point, so considering here from -1 to +1, we've got positive gradient in this section. And again, the graph starts off being just a little bit positive, but then as it moves to the right, it's getting steeper to the point where at x equals 0, the gradient's quite steep, right? So it might be doing something like, you know, coming up just a little bit here, but then when we get to x equals 0, we've got a pretty steep gradient. After x equals 0, as we go from x equals 0 to x equals 1, you can see we've still got a positive gradient, but it's gradually flattening off, right? And as we get to x equals 1, it comes down to 0. So the gradient in this little section must actually, it's still positive, but it's now coming down. It's coming down towards 0 again. Okay, so in this section, we might be getting something like that happening, okay? So gradient positive throughout the whole section from -1 to 1, but you can kind of see where the gradient is more positive and where it's coming back towards 0. Okay, this next section from 1 to 4, we've got negative gradient, right? Again, the gradient starts off by being just a little bit negative, so just a little bit below the x-axis. Then it gets fairly steep, right? And somewhere in this section, it then starts to sort of flatten off again and it comes back towards 0. So we get maybe this kind of thing happening. And we know that it comes back to 0 when x equals 4 because the gradient is 0 at x equals 4. So in this section, well, we're getting this sort of thing happening maybe. Right, we know it's going to come back towards x equals 4. After x equals 4, so we know it's going to come back to 0 when x equals 4, but after that it gets negative again, right? And again it gets a little bit negative and then really negative. So what's going to happen is after x equals 4, as we keep moving to the right, the gradient is getting a little bit negative again, then a little bit more negative, and then really, really negative. And so what's happening is that our graph of f dash of x is going to come up here and just touch the x-axis because the gradient does get back to 0, but then go down and be negative again. Okay, so if I try to make that look like a reasonable curve for our graph of f dash of x, we're going to get something that looks like this, right? And continues off in both directions. Now, those aren't going to be perfect. I don't know if that's exactly the curve that would match this original function. I don't know if that's the exact curve for f dash of x because I didn't have the rule to start with. But most of the time in these sorts of questions, that's about the level that you need to sketch to. You need to show where the stationary points are, which should translate into x-intercepts on your graph of f dash of x. And you need to really just show where the graph is positive and negative, okay? Very often these will be multiple choice questions, so that information is enough for you to decide which is the correct option. Okay, and on that note, let's have a look at a past exam question, and you can see what I'm talking about, although it's hard to get it all in one camera shot. So this question says, the graph of a function y equals f of x is shown below. So this is our original function, all right, if you want to use that phrase, original. Gives us a picture of a graph, doesn't tell us the rule, and it just says, which of the following could be the graph of the derivative function y equals f dash of x? Okay, and we got 5 options to pick from. So, what can we do here? Well, same idea as what we did before. You don't have to use this color coding every time, but it's helpful to see how it works just to start with. Let's look for our stationary points. Now, from what they're showing us, it looks like we've got a stationary point at x equals 3, or very close to x equals 3, and we've got another stationary point at the origin at x equals 0. So what we're looking for on our graph to try to determine which one's the derivative function, we need to have, remember that stationary points on the original match to x-intercepts on the graphs of the derivative. Now these are the only 2 points where the gradient's 0. So we should be looking for graphs where we have an x-intercept at -3 and an x-intercept at 0. So A can't be correct because it's got an x-intercept at -5 and 0. B could be, right? It's only x-intercepts are -3 and 0, so B is a candidate. C actually can't be. It's got x-intercepts at -3 and 0, but it's also got one at x equals -5, but there's no stationary point at x equals -5. So C is incorrect. D, okay, D looks like it could be an option because it's got a stationary point at x equals 3 and x equals 0, so it could be D. And E is wrong because we've only got stationary points at x equals -5 and x equals 0. So purely from the stationary points, we've ruled out 3 of the 5 options. We're just down to now thinking about, is it option B or is it option D? And the way that you can decide that is now to think about, okay, we've got our stationary points covered, but where is the gradient positive and where is the gradient negative? You can see that from, I guess, -infinity to -3, we've got positive gradient here. And in the other sections, besides the stationary points, we've got negative gradient. And so what we're looking for is the option that has positive gradient before x equals -3, which means the values should be above the x-axis. The values of the gradient should be above the x-axis. And that does happen in option B, but doesn't happen in option D. In option D, we're negative down here. Because remember, key idea, the y-axis is representing the gradient. Okay, so this one here, being above the x-axis, is actually giving us a positive gradient. Okay, so even with that information, we've got our options narrowed down, and by process of elimination, it's got to be B. You can just check as well that the rest of the graph seems to work out with what you're expecting. So we said there was negative gradient between -3 and 0, and the graph is below the x-axis here, which is what it's supposed to be for negative gradient. And then after x equals 0 and to the right, we've got more negative gradient, which means below the x-axis for the graph of y equals f dash of x. Okay, so always a good idea, even once you think you've picked the right option, just to check with the rest of the information to make sure, nothing's going wrong there. I hope that gives you a good idea of graphing derivative functions from the original function. But as always, get in contact with your teachers if you're getting stuck with anything. Good luck with your work.